Alright, today let's look at how to do a pre-stressed modal analysis inside LS-Dyna. This is a continuation from the previous video where I talk about the basic eigenvalue analysis and I did a comparison with Ansys Mechanical. We're going to continue this presentation slide deck with a pre-stressed analysis. I'm gonna use Ansys Mechanical as mostly a comparison benchmark. It doesn't mean it's right, it just means that we want to see the difference. Because I've usually done these frequency domain problem inside Ansys Mechanical, so I like to try to do that in Dyna. And by first of all understand the difference between the two code, and then to look at how they're different, how to manage the same different kind of workflow. Okay, so a pre-stressed modal analysis, I'm gonna go over the basic keywords and the processes. It's a very simple process. In a lot of ways, it is better than mechanical, and I'll do a quick demonstration between mechanical and Dyna just to show you. In a lot of ways, I think Dyna is actually more elegant in its implementations. I'm gonna do two examples. One is I'm actually not gonna do the third example. I'm gonna delete that actually. It's essentially very similar to the first two, which is why I didn't do it. First problem, I'm gonna do just a single beam. I'm gonna use a very simple cantilever beam to bend it. I'm gonna do a pre-stress analysis on the bent beam to look at how it's different from the basic analysis and compared to the mechanical. And I'm going to do a double beam analysis, which essentially I'm going to have a contact between the two beams while I'm bending them and then see how the contact is being managed. This really sets up the basis for more complicated problems, even though my example problem are very simple. I think it's a good way to look at it. And then, of course, I'm going to do a quick demonstration in the software, and I'm going to look at the results. Okay. All right, so look at keywords. Pre-stressed modal analysis in Dyna is called intermittent eigenfrequency. The reason they use the word intermittent is because you're actually relying on a load curve right here to define when to do the mode extractions, right? So you can actually, in a single input file, extract modes multiple times at a different stage of analysis, right? So in this simple example, I have a pre-stress stage, which is going from 0 to 1, time equal to 0, time equal to 1. And then I'm going to just essentially bend the beam. And then at time equal to 1, I'm going to extract 10 modes. But you can continue the analysis. Like I'm going to bend it more, then do a mode extraction again, or I can do other type of loads and do the mode extraction again. So every single time we decide to extract mode, you can define that inside this load curve, which makes this a very convenient way to do pre-stress modal, right? So instead of having to, for example, if you look at the basic mechanical workflow, right, as hopefully some of my audience will be familiar with, you have to drag the solution to the setup to generate a pre-stress modal for something like this, and I can open this up while we're talking about it. In Dyna, you can do it in a single input file. Therefore, you can just start with a normal transient analysis, then you do mode extraction, then you do transient analysis again, then you do mode extraction, right? It's not really interfering with each other. Nonlinear effects are linearized, just like mechanical, as you would expect, because it is a linear analysis. Okay, so let's look at the single beam problem first. So I have the results here. I can share in a bit, but let's look at the basic setup. In mechanical, which is I think is right here, right? So usually you have a static analysis. In this case, I just have some kind of load I'm applying to the one end. I'm fixed on the other end. As simple as it gets. There is nothing to it, and you can sort of see this is the deformation. Now with this, once you drag into a modal analysis, you have a pre-stressed state right here. Over here, usually you can do force sticking, force bonded. This is the mechanical way, right? And then once you do that, you get these mode shapes and natural frequency that you can sort of look at. Now, because the way mechanical works is that it is a wrapper around the actual solver, which is MAPDL, you actually can see, you can sort of see the beam is still straight and it's still oscillating along a straight beam. In reality, it's actually starting in a deformed shape, but you're not going to be able to see that in mechanical. So what you do is that you use this code template to basically display the information from APDL into the mechanical interface by posting these images, and that's all it's really doing. It's not doing anything that special. It sets the view, it sets the color, and you select the elements, and it's going to generate the view. That's all it is doing, right? And then you can sort of see in this case, you can't really do the mode shape display anymore in this view, but you can sort of see this is what it starts with, and you can sort of see the deformed shape is in a bend shape. And this is one of the limitation with mechanical in a pre-stress analysis, that you really can't see the actual mode shape. Now, if you look at Dyna, for example, this is the Dyna. This is the actual deformation plot in Dyna, right? I'm sorry, one second. This is the actual deformation plot in Dyna. This is the actual D3 plot. I got confused for a second. So you can sort of see this is where my final state of my deformed shape is going to be. And then over here, I can actually look at the different mode shapes, for example, right? So I can actually play this mode shape. And you actually have a deformed shape as part of your modal analysis, right? You can actually see the deformed shape, and then that's where the natural frequency is with respect to actual deformed shape. And that's one of the beauty with LS-Dyna is that you can actually get the results this way. So looking at how Dyna handled this, let me open up my example problem real quick. So you can sort of see what we do is that you basically import this code template into LS-Dyna. This is my implicit code template, right? So you still, if you remember from the previous video, you still require the implicit analysis. But in this case, this parameter is going to be negative, and it's going to call a load curve ID of 99A. And when you call the load curve ID, it's going to run an analysis from 0 to 1 second for the actual preload. At 1 second, it's going to extract 10 mode. As easy as it gets. It really cannot be any easier, in my opinion. You apply a force, you apply a fixed support. Man, MPC. Oh man, I just lost the word. I can't believe I just lost the word. The fixed support in this case. Hold on, I'm gonna check. I apologize. I'm gonna double check something. SBC support. Yeah, I just lost those 3 letters for some reason in my head. Yeah, so this is the SBC support, and this is the force. This is the nodal force that you're applying to these surfaces, and then you have a deformed shape, and this code template allows you to extract the mode shapes in a deformed shape, just like you can see in all those parables right here, right? Like this right here. And if you look at the results, right, you get a pretty clean result. So this is the deformation. They pretty much match on between the 2 code. This is the natural frequency and the mode shape. They basically match perfectly to each other, right? So which means in a pre-stressed modal analysis, without contact, the 2 code are generating essentially exactly the same results for all intention and purposes. That's good to know. Now let's look at what happens when you have 2 different beams. Now with 2 different beams, I essentially have a situation that looks like this, right? So this is what I've generated. So you can see in this is mechanical, right? So I start with mechanical. I basically have 2 different fixed support, one on each side of the beam, right? And then I'm applying a displacement BC on this end such that it pushes on this beam, it deforms down, pushes on this beam, which in turn deforms it. And what you get is a situation that looks like this, right? So you have a double deformation that has a contact between the two beams, and that's the behavior I want to be able to model. Now you have to realize, right, with the mechanical it's very interesting because the penalty stiffness over here I set it to be very, very low, right? There is a FKN factor that I set to be very low to get an easy convergence. In Dyna, it's gonna behave a little bit differently in terms of the actual contact stiffness, and I'll explain that in a bit, which is likely why I have a discrepancy in my results is because the way the contact is treated is different, right? The penalty-based contact is different between the 2 different code, and this is why we're gonna see a different result. But the deformation-wise, it looks exactly the same, right? So if you look at the deformation height is 75.575, and if you look at the Dyna version, and I'll talk about in Dyna version in a second. So let me pull up the Dyna version. The LS-Dyna version is there's a couple different ways we can do it, right? So let's go back to the slide deck real quick, right? Now with the two beam situation, contact is the main difference, right? So as you can imagine, in a lot of pre-stress modal analysis, right, you have to account for the pre-stress, but you also have to account for the contact that's established due to the preload. And contact are linearized in a frequency domain analysis, in a modal analysis. Right, there are 2 types of contact that's very common, right? You have a frictional contact, which is automatic surface to surface, but you also have a mortar contact. Mortar contact is it's a recommended contact method for implicit, and I'll explain the difference in a bit. But basically, the mortar contact end up actually behaving better. It aligns better with what mechanical is doing in terms of the contact treatment. And there's a couple different type of contact parameters that also affect the result in a very slight way that I've tested. I didn't present it here because the differences are so small, but each of these factors also have some impact, right? So if you look at the two different contact, one is the basic automatic contact, one is the mortar automatic contact. This is a standard frictional contact automatically generated by Workbench. So if you use Workbench, this is what's generated. You can also write it yourself. A mortar contact is mostly recommended for implicit analysis, even though you can use it for an explicit analysis. It is penalty based, segment based contact, and it allows sliding within each step of the implicit analysis, and that gives you a little bit of a room in terms of getting better convergence, which is one of the reasons that we use it. And I can skip ahead a little bit. You can sort of, this is the basic penalty contact and non-mortar contact in terms of the penalties stiffness, contact stiffness as a function of penetration. Over here, you just have a slightly different behavior. Interesting about the basic automatic contact is that before you reaches the zero penetration point, which is the contact point, you actually is already starting to build some contact stiffness. Whereas the mortar contact starts at always going to start at zero, and it's going to ramp up based on the amount of penetration distance. Right, so it is a slightly different type of contact treatment in a very minute way, but this is from the implicit guideline that I copy pasted here, which is very good to remember the difference between the two, and this is why we're gonna see what we're gonna see next. Okay, so if you look at mechanical and Dyna, you get pretty much the same displacement, no surprise there. But if you look at between mechanical and Dyna, the lateral frequencies start to diverge pretty significantly, right? And one of the reasons for this is that I can show you is if you look at, this is the first mode at 364 hertz, right? You can sort of see this is the, I guess you can't exactly see it because it should be in this manner. But if you look at, you can't really see the mode shape deforming because of the way that this thing works. But if I show you the LS-Prestressed model, right? So in this case, the first mode behave like this. You can sort of see that sliding that occurs right there. That's a 411.3 that doesn't exist in mechanical, and that's a completely different mode shape for the first mode. The mechanical first mode does not look like that, right? This is the mechanical's first mode. You have to sort of imagine this thing's bent, okay? This is why it's kind of silly because you can't exactly see it's bending. But if I were to use the mortar contact, which thanks to the recommendation from one guy from Ansys, I got that information from him. You can sort of see this now matches much better. This is the first mode of a pre-stress analysis, and this is with a mortar contact. You get a much better matching. You get a mode shape that matches with what mechanical is doing. Now you have to think about, do you expect this contact point to be sliding or not sliding? In this case, it's basically not sliding. And if that's the case, that's the right mode shape. If this is the mode shape that you expect to behave in your model, in the real application model, then this is the right mode shape. So this is where we have to make the judgment about what is the correct mode shape we want to extract from the simulations, right? Just understanding different contact treatment give you different mode shapes, and that's the most important takeaway for a pre-stress modal analysis where contact is linearized. The contact treatment really changes the mode shape, and we want to understand how it works. And as a last point to make, right, the FS, the static, dynamic, viscous, these terms, as well as the soft parameters, penetration parameter, these all have some effect on the mode shape and the natural frequency, but not in nearly as significant of a way as the type of contact we're using for this kind of 2-beam problem. I'm using the 2-beam problem as a way to demonstrate pre-stress modal, right? Because any other problem follow a very similar general logic behind how it works, how the solver treats these type of inputs, and how the response will be generated as a result, right? So we want to understand from a simple problem perspective how contact is working, and the key takeaway here is that automatic contact and mortar contact give you pretty different modal analysis results, and we want to make sure we observe the mode shape to know which contact type is best suited for our applications, and that's the way we can look at it. Okay, that's the end of the second video. This is the pre-stress modal. The next set of video, I'm going to be doing a random vibration, harmonic analysis, and shock analysis by using the modal analysis results to do a mode superposition method. This is a very, very commonly used method inside Ansys Mechanical, and I'm going to do that in LS-Dyna as a comparison and also as a way to leverage the better capability of LS-Dyna, but while also be able to do what Mechanical does pretty well, which are these linear dynamics problems. Okay, thank you very much. Hopefully it helps.